recording. Okay. So in the binary arithmetic, and let me try to expand this guy here so we can see. Binary arithmetic, we do the main, let me see if I can. Actually, I have to move this right here. So this is the basics. Of course, you know how we do the decimal arithmetic, the addition. We know that very well. In the binary, because we have two digits, only 0 and 1. So we have all the possible combinations: 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. And 0, 0 is 0, 0, 1, or 1, 0 is a 1, and 1, 1. The result actually, if we think about it, it's 2. It's 2. And in binary, the 2 is 1, 0. So if I am adding 1 plus 1, this should give me the 2, which is 1, 0. But because it's a single digit addition, we take the result. The sum is a 0. The sum is a 0 right here. And so this is, let me call this the sum, which is the result. And this one is carry into the next stage. Just like when we add 7 plus 1 is 14, 4, and we carry 1 to the next level. That's exactly what we are doing here. So that's what it is here. So carrying 1 to column is equivalent to adding 1 to that column. So if we do the add, I have these two numbers. Let me rewrite them myself. Okay, let me rewrite these numbers here. So I am adding plus. Now the 0 is the sign. So I forgot the sign. 1, 1, 0, 1, which is really, this is 11 in decimal. And I am adding plus 1, 0, 1, 1. Oh, I'm sorry, 1, 1, 0, 1 is 13 actually. So this is the 13, and this one is the 11. So the result should be 24. So when we do the addition, so I take this one plus this one. So I know it from my previous slides, 1 plus 1 is a 0, and there is a carry. So this is a 0, and the carry, as we said, it's on the next stage. So I will have, oops, I will make this carry right here, and I will put it in blue, so I know that this is a carry. Make it dark. Okay, so 1 plus 1 . Oh, sorry. Probably that's better. So I'm adding 1 plus 1 is 0, and there is a carry into the next stage. Now I am adding 3 digits, 1 plus 0 plus 1. Again, this is 1 plus 1 is a 1. So this is a 1. Oh. And again, there is a carry. There is a carry right here. So now I have 1 plus 1 is a 1, and there is a carry. Then 1 plus 1 plus a 0, again, it's a 1 right here. And there is a carry. And lastly, now here there is something new, which is 1 plus 1 plus 1. So again, this is in binary, it's the in decimal, it's the 3, and it's 1 1. So I will add a 1 here and have a carry right here. But this carry now is insignificant. And I am done. Now 1 plus 0 plus 0 down here, it's a 1. So why did I have 4 ones? I think 1 plus 1, 0, 1, 1, 1. Oh, 1 plus 1 is a 0 here. Okay, I got it. So there is a 0 here. 1 plus 1 is 0. 1 plus 1 is a 0. It was not a 1. And then 1, 1, 1. It's a 1. And 1 plus 0 plus 0 is a 1. So this is my result. And this result is 24. So that's how we do the binary arithmetic. Now, of course, this is very simple, but later on when we do the digital design, we'll find it very handy, this thing. Okay. So with the subtraction, we do the same thing. You subtract 0 minus 0 is a 0, 0 minus 1 here. Actually, what you do, you borrow like here. You borrow 1, 0 minus 1. So you borrow a 1 from the previous. So which is 2 minus 1 is a 1. So I have 1 here, but the previous column, you must subtract 1 from the previous column. That's what we call a borrow. And the other ones are straightforward. 1 minus 0 is a 1, 1 minus 1 is a 0. So let's see how we do that in using some numbers. So this is 1, 1, 1, 0, 1, which is, how much is this? This is, what's this number in decimal? So this is 7 times 2, 14 times 2, 18, or times 2, 28. This is 29, I think. This number is 29. And this is 2, 4, 8, 16 plus 3 minus 19. So 29 minus 19, the result is 10. How do we do the subtraction? We take the first one here. This one right here. Minus the this one, and then we will do the rest the same. So 1 minus 1 is a 0, and then the 0 minus 1, I have to borrow 1, guys, so there is a borrow here, so indicates a borrow. So we got this one. When I borrow from this one, this becomes a 0, because I took this one, I moved it to the right, so it becomes a 2 minus 1 is a 1, and then I'm left with a 0, 0 minus 0 is a 0, and then 1 minus 0 is a 1, and 1 minus 1, the last one is 0, so I have 1, 0, 1, 0. That's what that's how my number is done. Now, if I do, this is another example with lots of borrows. So this is 2, 4, 2, 4, 8, 16 minus 3, and the result is 13. So I take 1. If I subtract it from a 0, I have to borrow a 1. But this one, this 0 doesn't have a 1. So I keep moving this 1 all the way to the left. So this becomes 1. So 2 minus 0, or this is a 1 minus 0. Oh, I'm sorry. 1 minus 1 is a 0 because this is 1. So it's a 0. And this is 1 minus 0 is a 1. 1 minus 0 is a 1. And the last one is a 0. So that's how the borrow propagates all the way from here, right here. And once this propagates, then this one becomes a 0. My first one becomes a 0, and the rest becomes all ones, as it shows here. So this is the subtraction. Now, later on, we will find that this type of arithmetic is not easy to implement. It's expensive to implement in digital logic. So we need to convert the subtraction into addition. Do I have that here? Okay, no. Let me do a slide here. Change, subtract to add. I'm not going to do that now, but I will show the benefit. In the computer system, you are well aware that the central processing unit is our major computing system. That's where all the computation takes place. And of course, there is a memory somewhere. And the memory includes the cache and main memory, and later on the hard drive. All of this is considered. And there is some I/O, which is like the mouse, the keyboard, etc. Now, this CPU, the designers of computer systems have managed to make the CPU actually is an adder, or I would call it a parallel adder. So everything in my computing system is done through adding. I don't have a subtractor, I don't have a multiplier, I don't have a divider. All we have in the system is an adder. So that's why it becomes very handy, very handy. We use this here. Should be able to convert, subtract into add, so make the subtraction through addition, convert, multiply now into series of adds, which is true. So it's series of adds. Now the divide, when we divide things, we can easily do the conversion of the divide into series of subtracts. And the subtracts we have just said up there, it's an add. So eventually, it's a series of adds. So We have the, and of course the add is an add, summation, which is sum. When you want to sum things up, it's add. So see, I have all of these. I have an add here, an add here, and these are all our arithmetic operations. Now, if you tell me, oh, what about differential equations? Or differential equations are nothing but really subtracts, series of subtracts. What about the summation? Summation from I equal 1 to n, it's adds. What about the multiplication? What about the integration? It's add. And then there are products. So all our operations are nothing but sum, subtract, multiply, divide, and all of these can be converted into add. So we have here, all we have in our processing unit is an adder. Some people, they call it accumulator, which is accumulates the results of the add in it. And that's the power of using data representation, which allows us to do this type of arithmetic operation. So all our, in fact, if you come to think about it, when you have all your systems in the computer, including your databases, your algorithms, your mathematical models, your artificial intelligence, eventually at the CPU, they are all converted into an adder. Very powerful concept in the digital design, which made our life very easy. Now this is, again, it's another example for the subtract. Multiplication now, the binary multiplication, if I want to do the multiply, this is the truth table. We call this a truth table, multiplication table for binary. This is, we call it truth table for binary, which has the 0 times 0 is a 0. All the multiplication are zeros except for 1 when you multiply 1 by 1, and the rest are zeros. If we will do the multiplication per se, if we are not doing the adds, but in reality, when we perform the multiplication algorithms, we will be using the adds. Now, in order to add, you have to take the values of your multiplier and multiplicand, and those values, we'll use them in binary, something like this. Look, this is 1101 multiplied by 1011. We take one bit at a time. This is my multiplier right here. This we call the multiplier. So the multiplier, we take it one bit at a time, and we do the first bit 1 times 1101. The result is 1101 because 1 by 1 is a 1. So in our multiplication algorithm, the way we will do that, I will, well, let me finish this and then I will say what I wanted to explain here. Okay, so we take this, we take one bit at a time. So this, the first bit, I multiply this first bit by the multiplicand, one bit at a time. So this is, you multiply these two bits by using the truth table, which is 1 and 1, the result is 1 over 1. Then the 1 and the next 0 is a 0. So I have my partial result here. 1 by 1 is a 1, 1 by 1 is a 1. So I have 1101. If I have the least significant bit is a 1. Now I do the next bit, but here I do a shift to the left. I shift, so that's actually if I want to be more accurate, there is a 0 here. So when I'm shifting this guy to the left, as if I'm multiplying it by 2. So this is shift left, I will call this. I'm shifting my result 1 bit to the left. So my result now is 1101, but shifted to the left. Then I have the zeros. 0 multiplied by all of these is all zeros. Also, this is shifted to the left. I shift this guy to the left. And then lastly, I have the last one, which is the most significant bit, the largest in the multiplier. I have 1101. And then I will add these partial products. We call these, each one of them is called partial product. This is partial product. It's the product using 1 bit of the multiplier. This partial product 1, call it partial product 2, shift it to the left. Then I have partial product 3. Then I have partial product 4. So I have 4 bits in the multiplier. So I have 4 partial products. The first one, I get it at a certain level. Then I start shifting every partial product to the left 1 bit. I don't need now to use this one. Okay. And then I add all the partial products. Actually, I do need it. So this is 0 here. Oops. So when I shift this, I shift actually 2 of them. So I have 3 zeros here. And then here I have a 0 and a 0 and a 0. That's so I'm adding now. When I add, I have 1 plus 0 plus 0 plus 0 is a 1. 0 plus 1 plus 2 zeros is a 1. Then 1 0 0 0 0 is a 1. That's my third bit. My fourth bit now here is 1 plus 1 plus 1, which is 1, and there is a carry. Then 1 plus 1 plus 0 plus 0, that's a 0, and there is a carry. And then 1 plus 0 plus, I messed up here. So first bit is 1, the second bit is 1, the third bit is 1, the fourth bit is 1, and the fifth bit is 1 plus 1 is a 0, and the sixth bit is 0 plus 0 plus. Why do I have a 0 here? I should have a 1. Probably I'm better off if I fill those numbers with zeros so that I know what I'm adding. Okay, and here there is a 1 here, a 0, and then there is a 0, and there is a 0 here, is happening here? There is 0. Okay. Now I think I'm set. So I have 1 here. There is a 1 here. There is a 1 here. Here I have 1 plus 1 plus 1. It's a 1, and there is a 1 in my carry. And 1 plus 1 now is a 0. And there is a 1. And 1 plus 1 here is a 0. And then there is a 1. So this is correct now. Okay. So this is when I add all these partial products. And of course, I augment from the right with zeros and from the left with zeros. So I have 7 bits plus 7 bits here, 7 bits here, 7, 7, 7. So I have an homogeneous system. So I have to make sure that everything is lined up. So the result is, how do I get this? The way I do that, I say 2, 4, the second 0, 8, 16, 32, 64, 128, plus this is 15. 128 plus 15 is 143. That's how I make the simple conversion from binary into decimal. Now I can do the same thing, which is 1101 times 1011, with the when I do the 1101, instead of shifting to the left, I shift to the right here. So I keep all my numbers are lined up right from the very beginning. So I have 1011, and then the 1101 is shifted to the left, and then all zeros, then 1101 all shifted to the left. And I do the addition now in the same manner, and this is how the computer does it. This is how we do it. I will explain this later on when I talk about the computer. Okay, so now this is binary arithmetic. When doing binary multiplication, a common way to avoid carries greater than 1, because sometimes you have a carry. If you have, let's say, four partial products, then you expect in the extreme case here, let me do an extreme case of the multiplication. You may have in your partial products 1 0 0 0 1, let's say, and somewhere here you have 1. Let me make this 1. Actually, that's not the way I want to do that. I'm better off using my trick here. So I could have my partial product as 1 0 0 1 1 1. Let's say I have actually, let me do one more. And my second partial product, it would be, let's say, 1 0 0 1 0 1 0, let's say, because it's shifted. And then here I have 0 would be 1 1 1. I need this 1. Then it's a 0 0 or 1 0 0. It's 1 0. And then I need one more. It's 1 0 0 1 0 0 0. Now, what I wanted to show is that I could have in my worst case, if my multiplier if my multiplier is 4 bits, so I would have 4 partial products, and here I could have 4 ones. Okay, now the 4 ones also, if I have a carry from the previous, let me make this 1. Well, let's keep it 0 for now, and I will show in a second why I need it to be. So here in this, the red one, if I add these up, they add up 1 plus 2 plus 3 plus 4. This becomes here my result is 0, and my carry will go here into this. So this becomes 0. That's the first carry. I have 2 carries. That's a carry. And I have yet a second carry. Doesn't like it. So let me just do it this way. And there is a third carry now. Carry, which is 1. So this comes into, okay. So from the 1 plus 1 plus plus 1, I have a sum. This is my summation. And there are 2 carries, because when I add 1 plus 1 plus 1 plus 1, the result is 100. It's 100. Now, in the sum, I only have 1 bit as a sum. So this is here. I will say sum is a 0, and I have 2 carries. And carry 1 equals 0, and carry 2, second carry equals 1. Now it's also possible, because of a carry from the previous stage, I could have a 1 which is carry from previous stage, plus 1 plus 1 plus 1 plus 1, which are, that's my original partial product, which is 5, 101. So that gives me my summation is 1, the first bit, which is this guy. That's my sum. And I have 2 carries. Carry 1 equals 0, and carry 2 equals 1, which is, this is my first carry and the second carry. And the sum. The sum is in red, blue is first carry, and pink is the second carry. So that's what we need to take into consideration in our multiplication. Okay. So that's what I have just done now. Let me see where I am. Okay. Here, that's what we'll say. A common way to avoid carries greater than 1 is to add in the partial products 1 at a time. See, what instead of adding these 4 numbers, I will add 1001111 plus 1001010, and then I add these numbers and I get a result. I get first result. Now, because these are 2 bits at a time, the maximum I could have will be 3 bits, which is the maximum carry. 1 plus 0 is a 1, 1 plus 1 is a 0, and there is a carry 1. 1 plus 1 is a 0, and then there is a carry into this fourth stage. I have 1. That's the maximum I could have right here is a 1. Now if I will just do the, so this is 1, and the previous one is a 0, and there is a carry here, 1, and 1 plus 1 is a 0, and this is the carry right here. I have the 0, and the carry from here goes all the way right here. That's my carry. It comes 1. And now I have 1 plus 1 plus 1. That's the absolutely maximum numbers which I have. So which is 1 plus 1 plus 1 is a 1. So there is a 1 here. And there is a carry right here. So there is a carry. So I only have 1 carry into the next stage. I don't have 2 carries, not like here. Here I have 1 plus 1 plus 1 plus 1. There are 4 ones. There is 0. Carry number 1 and carry number 2. Actually, carry number 2 is a 1. Here I don't have that. Okay, so I have 2 carries here. So we said to avoid these 2 carries, instead of adding 4 partial products, I add 2 partial products, and the 2 partial products, the maximum number of carries is going to be 1 carry into the next stage. That makes the life of our adder simpler. When I build my adder, it's going to be much simpler than making an adder with 2 carries ahead. And that's what we say here. That's the slide about. So when doing binary multiplication, a common way to avoid carries greater than 1, which means the number of carries is only 1 to be, to add in the partial product 1 at a time, like here. So 1, 1, 0, this is the same example. The first partial product is all ones. The second partial product is all zeros. Let me add them first, we say. So I add 1 plus 1, 1, 1, and a 0. So that's my current partial product. Now, I do the third partial product, which is 4 ones. So I get the 4 ones shifted to the left 2 bits, and I make the addition. Now, my final partial product, I will add the 1, 1, 1, 1. Excuse me. So now this is how we do that, the final partial product. So the idea here is I only add 2 partial products at a time, but instead of having, like here, one add. So if I have these numbers which can be added in parallel, I could design an adder that takes 4 partial products in parallel, and I make the addition. It's going to be a bit more complicated. But the other way, I would say I don't need that. I'll just do multiple adds. I would say add number 1 here. This is my first add. That's my first add. So I would say add 1. Okay, and then my second add. So I added the first partial product to the second, then I add to it the third partial product. That's my add number 2. This is add number 2. And then there is excuse me, the third add right here. So in general, I could generalize this here. I'll duplicate the slide and I will do total number of add operations is n minus 1, where n is the number of multiplier bits, or actually we call it the size of the multiplier. So if the multiplier has, let's say, 10 bits, then we will use 9 add operations. Actually, this one I don't need it because I had it on my previous slide. And those ones, I'll just say add 1, add 3, all the way here. Will be add 9. So I have 9 adds. Now, another trick which we use in digital logic design, if I have 2 numbers, for example, here, if I am multiplying 1101010 times 10110. Now I choose to have this my multiplier, the shorter. Why? Because I want to reduce my number of adds. So I will say choose or make the multiplier, because I can do it both ways. Make the multiplier 101101, which is how many? 6 bits, and therefore it's 5 adds. And make the multiplicand, which is the big one, 11010101010. Now this becomes my partial product. My partial product is either this number or a 0. And now this is, it depends on my adder, how many bits it can add in one shot. In a 64-bit machine, this can be up to 64 bits, or actually it's 63 bits because 1 bit is going to be for the sign. And the multiplier, I will always pick the shorter as my multiplier, because that means I reduce the number of adds. So if I picking the shorter number as my multiplier will reduce we reduce the number of add cycles, I would call it, because each one is going to be a cycle. So those are just simple tricks used in the in our dealing with arithmetic operations. So since I can do every time I make I multiply this one with this guy, that's number one. Then I do 0 multiplied by this. Now note that if it's a 0, I will just make the partial product equal the first one shifted to the left. So in essence, another trick here is for the multiplier, you need, actually here, you need only to add when the multiplier bit is 1. When the next multiplier bit is 1, you have to add. If it's a 0, you just shift. If the next multiplier bit is 0, just do the shift. So therefore, I will modify my definition here. Total number of add operations, I would say maximum number, not total, maximum number of add. Why maximum? Because I could have is n minus 1, where n is the number of multiplier bits. And if the multiplier has so many zeros, then it will be the maximum number of add operations is equal to the ones, equal to the bit which have the value 1 in a multiplier. I don't have to do the addition, the add operations whenever the multiplier bit is a 0. I will just do a shift. So that's why we have in the adder, in our CPU, our adder is capable of doing a shift left or shift right. In this case, it's a shift left. When we do the division, we do the shift right. Okay, so those are the tricks in digital logic which allow us to do our arithmetic operations as easy, simple, and fast as possible. We first pick my multiplier to be the shorter. Then if it's the ones will be multiplied, or I will have an add for the partial product, and for the 0 I will just do a shift. Now there are some people who are very greedy. They really want to take the simplification and to gain time as much as possible, this is a good greed, by the way. I would say greedy algorithms. So let me see if I can do that. Assuming that I am multiplying, let's say, if my multiplier is, let's say, 1, 1, 1, 1, 1, okay, which is all ones, multiplied by a multiplicand, which is large 1, 0, 1, 0, something like this. So now here, I need to do 2, 4, 5, because all of them are ones, need 5, actually 4, I'm sorry, because it's n minus 1, 4 add operations. Now, the trick which they used, this 2, 4, 5, actually, my 1, 1, 1, 1, 1, I could write it in as 2, 4, 8, 16, 32, because this is 31 minus 1. So this is this guy. So if I do now the multiplication, I do multiply now. Instead of all 5 ones, this 32, 2, 4, 6, 18, multiply by that number, by this number. So I just converted my adds into only one add because all of these zeros are shifts. And then once I get the result, once I have the final or the semi-final, I will say semi-final result, then I will do my final result will be equals, let's say, this is actually, if you think about it, it's this number shifted to the left 1, 2, 3, 4, 5 times, and this is the one. Actually, it's shifted to the left 5 times. That's what it is. And then the final result will be this guy. Let's say this is z equal my final result then will be z minus 1. So I'll just do, so just converted the 4 add operations into 4 shifts to the left and 1 subtract. And the subtract, of course, again, the subtract is an add. So it's actually 4 shifts and add and an add. That's how I would call them the greedy algorithms in digital logic. And those, sometimes you'll see if you convert this number into main zeros and then do the subtract, if the number, let's say here, I was able to do to save a lot. But if my number was, if my multiplier had this thing like 1, 0, 1, 0, 1, 0, 1, 0, then you are not going to gain if you convert this because you will still have the same number of ones no matter what. So 1, 2, 3, 4, 5 ones, so you have 5 adds. If you want to convert this to subtract it from the binary number, this is going to be what? 2, 4, 8, 16, 32, 64, 128, 256, 512. So this is the 512 minus this number, you are going to get the same number of ones anyway. And of course, as I said, the greedy algorithm say, okay, no matter how much I can save, if I have here this one and this is a 1, I'm pretty sure I am going to save if I do the subtract. Okay, let's do the division quick here. The division, the binary division, is very similar to the decimal division, except it's much simpler. I have my divisor here, which is 1011, and the dividend is 100, 1001. Because this is 4-bit, I will take 4-bit at a time. So I take the first 4 bits, 1001. Now those 1001, just compare with the divisor. This is less than this number, so I go to 1 more bit. So I take, this is 10010 is larger than this, so the quotient is going to be 1. You multiply this by 1011, you make the subtract operation, you get 1111, you bring down the next 0. So now this number is less than this number, so you get, I'm sorry, this is larger. This is 2, 4, 8 plus 6, this is 14, and this is 13. So I get a 1 here. I do a subtract, then I get 1 more 0. 110 is less, so I put the 0 there, and then I get the final 1 down here, and the result 1101 by 1011. It's 1, and then you subtract. You no longer have any dividends, so the remainder is 10, and the result is 1101. This is very similar to the, as I said, to the decimal division, except that now in decimal division, when you have a number like 145 divided by 11, you want to see what is the remainder. The remainder could be from 0 to 9, whereas here the remainder can be either 0, oh, I'm sorry, the quotient can be from 0 to 9. Here the quotient can be either 0 or 1. And then, of course, the remainder you have to subtract it from the original dividend. Okay, now quickly, representation of negative numbers. We said there are 3 different ways of the sign magnitude, which means I get my number, I put the sign, I give it a bit 0 or 1, 0 for positive and 1 for negative, or I use 2's complement number. And the 2's complement, actually, you take the power of 2 for the number of bits, and you subtract from that your number. So this becomes the 2's complement. And the 1's complement is when you complement every bit from 0 to 1 and 1 to 0. And in each of these, the leftmost bit of a number is 0 for positive number and 1 for negative, all of them. So if my number is, let's say, minus 7, so this is going to be 1. If I have my 4 bits for my integer, for my number, so this is 0, 1, 1, 1. And if it's 2's complement for the same thing, minus, I said 7, oh, this is 7, I said. So this is 0, positive. And if I will do the negative, then it's 1, 0, 1, 1, 1. This is signed magnitude. Signed, which is the magnitude, keep it as is and give it 1 bit to be signed. And if it's 2's complement, or 1's complement, let's make it first. You just take all of these bits, the 5 bits now, not the, so you take the 1, 1, 0, 0, 0. So that's my 1's complement. If I have now total of 5 bits here, the 4 bits are the sign magnitude and the 0 is the sign, so I have a total of 5 bits. And the 2's complement is going to be 1, 1, 0, 0, 1. I'll show that in a second. So those are the numbers here. Most significant bit is the sign here. And this is minus 5. If I have 3 bits representation for my number and 1 for the sign. So in binary, this is 101. That's my number. And the sign is 1. So it's minus 5. It's not, I'm not going to read it as 13 because in 2's complement, this is 13. But with the sign, it's minus 5 rather than 13. And the numbers, how many numbers I can represent here? This is the, I'm going here again, this is my 1's complement. I convert every bit to the opposite. So it's 1, 0, 1, 0, so 0, 1, 0, 0, which is like the 4 is the 2's complement of the 5. And the 2's complement, now I just add 1 bit. I add 1 to this number. So this becomes 1, 0, 1, 0. So it is 0, 1, 0, 1. And the number is 3, minus 3. So if I add minus 3 plus 4, the total is 7 because that's the maximum number I can have, or minus 3 plus 5 is 8. So what I'm saying here is the for signed binary integers, the word length is 4, total is 4, including the sign, Now, note that if I have 4 bits and I don't have a sign at all, this is an absolute number. So for 4 bits, unsigned, I will call it, unsigned, then I can represent 2 to the power 4, which is equal a total of 16 integers. I'm talking about integers here, which goes from 0, 0, 0, 0, all the way to 1, 1, 1, 1, which is 15. But if this is signed now, but if it's 4 bits signed, always the most significant bit is going to be a sign. So I will say, let's say 0, my sign, and I will mark it in red, this guy, so it doesn't count towards my number. And then my numbers go from 0, 0, 0 in positive all the way to 1, 1, 1, or 0, 1, 1, 1. Now, these are my digits, my real numbers. These are my numbers. And the other one is a sign. So I can represent number only from 0 to 7, not from 0 to 15. And that's what I have it here. So if I go the positive integers, the all possibilities, okay, so it's all 4 zeros all the way to 0, 1, 1, 1. These are the positive numbers. All I can represent is from 0 to plus 7. The negative numbers now, if I go here, so to be 1, 0, 0, 0, all the way to 1, 1, 1, 1. So this is the 1, 0, 0. It's very interesting. This is minus 0, which is ridiculous because we don't have minus 0, but nevertheless in the representation, that's what we have it. All the way to 1, 1, 1, 1, which is minus 7. So I can represent only, and the plus, of course, from 0 to 7. I can represent from 0 to minus 7 or from 0 to plus 7. In one's complement, the same. My number here is, which is negative. See the 1, 1, 1 in 2's complement. Where I will do that here. For the 2's, the 1's complement, the 1, 1, 1, since the most significant bit is a 1, so it's a negative. So because it's negative, I have to convert these to their original. So this becomes minus 0, 0, 0, 0, because I convert all of them to zeros, which is, that's a 0. Again, this is a minus 0. So the 1's complement and the signed magnitude, they have this number which is called the negative 0, which in reality, this is a waste of space because we don't have a negative 0. 0 is a 0, whether negative or plus. So the 1's complement, it goes from minus 0 here. I will call it minus 0 at the top, all the way to, you take this and you convert it, so it's 1, 1, 1, 0, so it's plus 7. So this goes all the way to plus, I'm sorry, minus 7. because it's a 1 here. So when I convert this, it's all 3 zeros become 1, 1, 1, 1. And this is the sign, so it's a -7. So it goes from -0 to -7. Note the 2's complement. Interesting, 2's complement does not have the -0. It starts from here, which is the -1, all the way to -8, because this 8 here, 1, 0, 0, 0, if you convert it, you do 1 plus 1 plus 1, I mean 1, and then you add 1 to it, it becomes 0, 0, 0, 1. So the 1, 0, 0, 0 is the -8, and the but we don't have a +8, we have +7 to -8. So I was able to save on the negative 0 for 2's complement. That's why when if I am asked why the computer systems they prefer 2's complement over 1's complement or sign magnitude, number one, we have one single representation for the 0, which is the plus, which is the 0, which is the +0. We don't have a -0, and then we have one more integer which can be represented for the 4 bits. We can use -8. Although we have the minus, no, actually, only the 2's complement has the -8. See this -8 here for the sign magnitude doesn't exist. For the 1's complement does not exist. We have it only for the 2's complement. And that's because we saved on the -0. That saving allowed us to represent yet one more number. Now, that's, of course, as I said a few minutes ago, in computer systems, the greedy algorithms are all over. If you save 1 bit, then you say, oh, you know what, this 1 bit, there could be 1 giga words, 1 giga words, which means 1 gigabits I have. If I save 1 bit, in each word, it's a 1 gigabytes. If in each byte I save 1 bit, so that's 1 gigabit. So it's a lot. So they go all the way to the extreme. So we don't have to argue with them. Oh, what's the big deal that you are saving a bit or an integer here? So that's where the greedy things are always there. Now the power of 1's or 2's complement is really to do the subtraction. So if you do x minus y, it's a straightforward. But if you do x minus y, it becomes x plus y. So we do the addition, and the minus y is in 2's complement or 1's complement. So we can, so my negative number is in 2's complement or 1's complement, then I should be able to convert it into an add without making any changes. I'll just add the 2 numbers and the addition becomes a subtract, and I will show the example for that. Okay. Let me stop right here. I don't want to go through the example now. I will make it next time, so we'll have more time to see the power of 2's complement arithmetic operations, and then we will go to the logic design. Okay, do you have any questions?
No questions.
Okay, thank you very much, thanks. So I'll see you next Monday, right? Or next Thursday, I'm sorry. So we'll see you this week, Thursday. And hopefully I will finish this binary arithmetic and binary representation next time. Okay, have a good night, guys.
You too, thank you.
Sure.